All right, so it is recording now. Um, it's odd. I don't know, maybe it's. Does anyone see where the. Is it just slideshow here? Oh, okay. Huh. That's not very intuitive. All right. So essentially, what the goal is today, because I'll be teaching three courses, is today kind of give you more of an overview about what goes into communications dealing with power systems. So really, most of today is actually just going to be vocabulary. And from that, we're going to kind of use that in the next couple classes to give kind of a broader look at what we're actually implementing right now. So everything we talk about today will definitely be a rehash from the communications course, the EET415, but it's still really, really important knowledge. And so those of you that have taken that course, you'll kind of see a lot of the stuff pop up that we've talked about quite thoroughly in that. But then the class for Tuesday, I'm going to go in depth into IEC 62850 communications, which is going to be something that's really, really big in the power industry in the next few years. And then on Thursday of next week, we're going to cover basically what needs to go into testing of these communication networks. So when we talk about protection testing, that's this whole giant segment that a lot of people are very knowledgeable in. Like before a substation goes online, you have to do certain testing and commissioning. We're going to be talking about that same idea, but from the standpoint of the network. And so that's what we're going to learn about on next Thursday. But today is, like I said, mostly just going to be vocab. So there's a term here I labeled the slideshow as the power utility communications. This is one of like seven different words that people will use for basically the same thing nowadays. So I just want you to kind of have this and write it down. But I could have just as easily called this session the SCADA session. I could have called it communications in general. Like there's a bunch of different terms. So this is a newer one that I've seen people using a lot is power utility communications. And it's a pretty broad term, but they're talking about specifically the protocols that we use in the power industry. And so, for example, I've heard this recently where people will call me like a puck person or a puck group. So that's the power utility communications puck. Um, so that's a really common term, but also you've heard this class, like these sessions probably being called like a SCADA session. That's a really similar terminology, and we'll talk about that. So here's kind of a list of everything that we're going to be talking about today. A lot of it is, like I said, just giving definitions for things. But I do have a couple pictures in here where we'll go a little bit more in depth about where we actually utilize these things. But at the end of this class today, you would want to be very familiar with all of these terms. Like these should not have any mystery left to them. So if at any point you have questions, if anything is not explained as in depth as you would like, please ask the questions because um, you really need to understand what these terms mean for everything else in the future to make sense. So this is just a list. Like I said, you have the slides, so you have this already written down, but we're basically going to go through slides that explain each one of these and talk about them in a little more depth here. All right. So the first one on that list, a lot of you that have already worked in the industry have probably already heard. But if you're not in the industry yet, this one seems a little weird, but it is a very commonly used term. So we use the term IED, Intelligent Electronic Device, just anytime we don't know the specifics of the thing at the endpoint, or when we don't really want to worry about what is that specific thing doing. So that's really actually helpful to us because what you'll find is when we're designing things, we don't always have all of the information like right at the point where we're designing. So if, for example, in this course you're doing protection, right? Then when you're designing a whole protection scheme, you probably have a general idea of what kind of elements that you need set up. Like you need maybe a differential element or line distance element, things like that. So you know you need relays capable of doing those things, but you might not know exactly how many relays you're going to be using or what brand of relays or even what type, things like that. So then when we don't know those things, instead of saying like an SEL 451 relay, we just say like some generic IED that can perform like line distance protection, something like that. So we use this term generally just to describe things where we don't know the exact item that we're going to be using. But it can also be used for a whole different, like, bunch of different types of devices. So don't always think in your head, like, in this course, you're talking about relays. Don't always think an IED is going to be a relay. That's not the case. So usually we describe it for like end devices. So they're the things that are kind of at the end of the chain. So like a PLC, a relay, a real-time automation controller, but then even a PC or a server could be an IED. Where things get a little more confusing is it is possible for you to talk about networking equipment as IEDs, because if you think about this definition right here, right? Intelligent electronic device, that could basically be anything, right? As soon as you throw a microprocessor in it, it's an intelligent electronic device now. But when we use this in power, we usually don't mean it for our network equipment. I don't know why we draw the line there, but that's just how it usually is. So if you hear this, we're usually talking about the things that are actually doing things at the end. So like something that's reading in values from a sensor or a relay or a server that's set up to capture data, something like that. So from a standpoint of our design, where we just drop in IEDs, what we generally care about more than like what is the exact IED we're using is what are the functionalities of that device that we care about. And that's where we kind of put it in a box as an IED. So we might even define it a little bit more in depth. So we might say something like on a big network diagram, you might draw down to like where all of your relays are, and then your relays, you would label them as like protection IED. And then you might have like an RTAC or a PLC, and then you could even say like a PLC IED or something. So we do that because we just want to indicate to the people that are actually looking at these diagrams later, like what was our intention. But still, we don't necessarily know what the exact things are. So we just want to give them the information that helps them understand why is that IED there. So if I was doing SCADA communications, we worry about certain protocols that we use, and I might want to label on there that we have like an IED that would be a PLC or something, and it's going to be using these certain protocols. But again, we don't really care who manufactures it, what the model number is, anything like that at that point. So that's where you'll see IED pop up all the time, especially really early in the design phase. And then later, as things really get figured out, they'll put the exact model numbers of things on the design later. So does that all make sense? Any questions about that so far? So this is the other really broad term that basically means the same thing as what was on the title slide here. So the power utility communications, when we're talking about in the power world, power utility communications and SCADA basically mean the same thing. I'm not saying they are exactly the same, but people use them in sentences as basically the same thing. So it can be a little confusing when you start out where the delineation is between what is considered SCADA and what is actually considered like protection and control. But once you work in the field for a while, it becomes very intuitive, actually. And the easiest way for me to kind of describe where things would become SCADA is when you have digital information leaving a device. So if we have like a protection IED, like a relay, sitting there and it's getting information from a current transformer or voltage transformer, we wouldn't really consider that SCADA at that point. That would just be protection. So we would be hiring a protection engineer to deal with that. But if we then hook up an Ethernet cable to that relay and send the data off somewhere else, or we have a serial communication cable and send that data somewhere, as soon as that data is leaving the relay, then we start talking about it in terms of SCADA. So that's where this whole big terminology comes from. So supervisory control is when over that serial or Ethernet communication, you want to operate something. Or on the other side, there's that data acquisition. It's where like the relay has information about the power system that you want, and you want to bring it out into a server, into sending it out to your control system, something like that. So that's where that terminology comes from. But again, it's really, really broad, and I like to just uses kind of more this definition that anytime your digital information is leaving the device. So it is also broad in terms of how do we actually utilize SCADA, like what do we send it on? And so we're not narrowing it down to like it can only be SCADA if it's over Wi-Fi or over serial or something like that. It's all SCADA. And the reason that we do this kind of terminology is we split it out into kind of job roles. And so in a normal utility environment, you have people that are labeled as like protection and control people, and then you have people that are labeled as SCADA people. And normally they don't understand 100% of what the other people do. And in many cases, the SCADA people know 10% of what the protection people do, and the protection people know 10% of what the SCADA people do. And then they have this 10% overlap where it's just they need to interface with each other, but everything else they want to kind of leave that off to their respective sides. So in terms of schooling or like the knowledge that you would need to be SCADA or protection, protection, it would be a lot more important for you to have like your power classes, your Laplace transforms, your overall like protection methodology, like zones of protections, things like that. That would be all things that protection engineers deal with. SCADA, on the other hand, would be much more like communications oriented. So they would be the people that probably have more of an IT background. They understand things like switches and routers. They understand more generally like programming, just communications in general. And so that's kind of where they diverge, even though they're both electrical engineers. And so then they have that 10% where they need like a SCADA person needs to know just enough about protection, about like why would a relay want to do these things. And then the relay people need to know just enough about SCADA to understand like, oh, if I want to move this information over here, this is the methodology that we'd use to move that information. The specifics of it, they don't generally worry too much about it. But at the end of the day, SCADA is just a really broad term that you definitely need to remember because it'll happen in a meeting or something. You'll go in there and they'll say something about SCADA. And I just want you to have that in the back of your head as you hear that term and you're just like, oh, they're just talking about communications. They talk about SCADA, that's what they're talking about. Weirdly, we also roll human machine interfaces, which I have a slide on that in a little bit, but basically that's like touch panels for controlling things. We roll that right into the SCADA people's job as well. I don't know why that kind of came about, why they do it rather than protection people, but that's how it is. Another really important one is hardwired. So the reason that I bring this one up is because it's easy to get confused on again where we draw the line on like what's SCADA and what's protection because a protection relay it's still taking in information, right? Like I just told you on the last slide here that like SCADA is when like you have digital information leaving your device. Well, you can have a relay capturing information as well, but that's not SCADA at that point, right? So when we have a relay capturing information, but we're not calling it SCADA, that's because the data is generally hardwired. So um, a common scenario in the real world, like unfortunately I don't have like a pen that I can draw on my screen with, but I'll try to do my best, uh, is like if we have a relay like this, hopefully this is somewhat legible. I have to draw with my mouse, so it's even worse than my normal handwriting. And so if we have a relay, then we would have something like out in the field like a CT. So I'll put that here as a CT or a current transformer. And if we're taking the actual data from this CT and running it back into the relay, this is going to be some sort of a voltage waveform on this line. So if we had this CT is hooked up onto a power line that's an AC waveform, you would see something like this as the voltage or the current. And then on the relay side, it should get a proportional representation of that from the CT. And so that would be a hardwired connection where it's still sampling from the actual power line. So you're getting current information, and then the relay can actually make its calculations based on that. So where this would be different than SCADA is if we were doing like this type of thing with SCADA instead, the CT would have to be converting this waveform into something that's digital, like ones and zeros. So we would get something like this that's sending the same information as ones and zeros, and then send it over a line like over Ethernet or serial to our relay, and have it receive it that way. So that would be kind of the difference between SCADA and hardwired in general. So the in the other really big thing with hardwired is generally we have like a one-to-one communication. So we have like a CT just talking to a relay or maybe another relay, where when we're talking about digital information, we can send it to a whole bunch of devices simultaneously and they can talk back and forth over the same wire, usually. There's obviously always edge cases that I can talk about that are that are not that case, but so hardwire is how we used to do everything before we had SCADA as an option. And now we're kind of in this weird point where we have mixed SCADA and hardwired systems. And so the reason why we don't just move everything immediately, or actually, that's a good question for you guys. Why do you think we still have a lot out there that is hardwired? Why haven't we just moved everything to digital communications and SCADA?
It's expensive.
Yeah, definitely.
And
So
labor would be expensive.
yes, definitely. So labor is going to be expensive because, I mean, we already have these systems up and running, right? And so if you want to convert it from what it was hardwired into a SCADA situation, you need to tear it all out, convert it into digital and everything, run new cabling. So if it's already working hardwired, why would you do that? So there are benefits theoretically to going into SCADA world, but for right now, what we're doing is working hardwired. So then but then there is the whole other side of the cost as well, that basically if we have a CT and we have a relay, we just run that one copper cable in between them to have our hardwired signal. Looking for the key. Uh, but if we are adding in like digital communications, normally we need additional hardware. So like we might need like network switches. We're going to need potentially management software, things like that. So you open up this whole new can of worms once you start dealing with SCADA. So a lot of people are hesitant to add SCADA into their systems, and there are benefits to it, and that's why we want to do it. But on the other hand, there are these drawbacks. And so there's, especially in the utility world, things are really, really slow. And so they're always hesitant to change anything until they absolutely have to. So we do have a bunch of options now for replacing things that we previously weren't able to. So this is basically the reason for that, is where we've had hardwired in for a very long time, even after SCADA came out, was for things that were needed to be very, very reliable and things that needed to be very fast. So that's essentially a limitation of network communications in general, is there's an overhead. So there's a delay when we're using SCADA systems. So if we look at this hardwired CT to this relay, what would you guess is the delay of information from the CT to the relay?
Nearly zero.
Yeah, I mean, we have physical constraints, right? If we talk about like in terms of physics, the universe has a speed limit, right? And it's the speed of light. So there's no possible way that we could get information from the CT to the relay faster than whatever the speed of light is. So then it just depends how far apart they are, right? But then obviously there are some additional concerns, and it's going to be slightly slower than the speed of light, but it's still pretty close. So there's no way for us to utilize like SCADA to go faster than that. This is already as fast as something could be. We're like at the very minimum there. So when we add in SCADA, there's additional overhead that goes along with sending the ones and zeros, and we get actually slightly away from that speed of light. It's still really, really fast, and the new stuff that we have is extremely close to what it can be done with hardwired, but historically that wasn't always the case. And then there's this other aspect here that's reliability. If you wire something like a CT directly into a relay, in terms of reliability, I mean, it's literally you have one wire that it works or it doesn't. So it's very, very reliable. where when you're dealing with network communications, then you're drawing in potential failure points. So can anyone guess, like, in terms of reliability concerns of a network versus reliability concerns of hardwired, where could you see some failures happening? Or why could there be more failures?
For example, in anything that's getting calculated, there can be errors in memory, just with regular radiation or any like miscalculation. Um, that just adds a little extra error.
That is actually that's an interesting point. Although something to think about along with that though is, do you think a hardwire has no error?
Not that it has no error, but it's a little bit different than dealing with a hardwire system where there is no computational error.
Yeah, I mean, so that is actually, I would actually almost say the opposite, that it's almost actually a benefit of sending information with SCADA is that you have less error. But we'll talk about that a bit more in detail. But I do see where you're saying so it's something that we have like electromagnetic radiation coming from the sun and stuff like that. And if you have ones and zeros stored in memory, it is actually possible for like a photon to come in and, or I guess not a photon, technically a stray electron to come in and like hit a one or a zero and swap it. And then your data gets all corrupted. And but you wouldn't have that same situation with a sine wave information that's like a voltage or a current. But where you can potentially have error with like a normal hardwire like this, where you're sending analog information, is there is always electromagnetic interference on a cable like this. So the longer the cable is, the more your signal is going to drop off. And then one second, guys, I need to do something here. Right, 1 second. All right, sorry about that. Um, so where the error can be introduced on a signal like this is then your waveform that you're expecting to look something like this. If it's a short line or you don't have like any electromagnetic interference, when it arrives at your destination, it's going to look exactly like that. But in reality, we actually see little waveforms riding on that, and it gets over time does get a bit distorted. And so we have to deal with that, and we have methods of when it's hardwired, like we know what our line distances can be and stuff like that. But we actually have to send it at a pretty high voltage and current. Generally, we don't use like low voltage values for this, so that we do get a high reliability. So it's an interesting point that you brought that up, because basically that's one of actually the benefits of using digital signals is this, where you see like these squiggly things show up on this line. That doesn't happen with the digital signal. That basically once something is converted from analog into digital, you're going to get the same value no matter how far away you send it. Like I could send the voltage value from Maine to China, and with a digital signal, it's going to be represented exactly as I had in Maine. It will be represented that in China, where if I tried to send it as an analog waveform, it's going to get distorted over the line length. So uh, in terms of accuracy, sometimes digital can be better, but yeah, we were saying about reliability here. So your point there is very valid, that the digital systems can have corrupted data, which is definitely true. The other big point I wanted to kind of get across there is that basically you're when you do things with SCADA systems, one of the reliability issues is you're adding in additional points of failure. And that's something we like to avoid in general, especially in the utility world. Like we don't want to have just one point where if that goes down, then nothing works. And so with SCADA, that's our networking equipment. So if we have a hardwired signal, basically the only points of failure are our CT, our wire, and then any terminal connections, and then the relay itself. If we add in SCADA communications, we're going to actually uh, I'm getting a, can you guys still hear me okay? I just got a warning that my internet connection was unstable. Everything
It
all
broke up for a second, but it's
okay.
stable now.
Okay. So
Yes.
when you add in SCADA communications, you're going to be adding networking equipment. So things like switches and routers, and each one of those that you add in the communication chain is one more potential point of failure. So that's where a lot of people are hesitant for like really secure systems that need a ton of reliability. They're hesitant to add in SCADA communications because they're worried about all those potential points of failure. And something we'll talk about when we talk about 61850 communications actually is how do we deal with that? Like what are our methods of even utilizing SCADA with these communications that can replace hardwired communications? So those are the two things about pushback that you'll get anytime you want to convert things from hardwired into a SCADA communication is those two aspects of reliability and then how fast is it?
It's breaking up a bit more now.
Okay. Hopefully it'll come back here in a second. As we get farther away from the airport, I think my connection will get a little better. Um, all right. So unfortunately, I was hoping this stuff would disappear on the next slide, but it looks like I'm drawing. I'm not even sure what I'm actually drawing on here, but um, the next definition that we have here is protocol. So this one is, again, as many of these are, it's actually a pretty broad term, but in communications, we use it for one very specific term usually. But I'm kind of giving you the background here of more what you want to think about a protocol as. It's not just like a technical description of something. So if you look up protocol in Oxford Dictionary, it'll say the original draft of a diplomatic document, especially of the terms of a treaty agreed to in conference and signed by the parties. So with that definition, how do you think that applies to communication protocols that we use in industry? Like, why do we call it then a protocol if this is, sorry about that. I think I just disconnected for a second. What was the last thing that I was saying about this definition, I'm guessing? Can you guys hear me?
Somewhere around there.
Yeah.
It was
Okay.
breaking up.
Okay. Sorry. So in terms of industry communications, why do you think we use a terminology protocol for our communication protocols? When this is like the actual Oxford Dictionary definition of what a protocol is. Like, how does that translate to what we use in the utility world? So there's one really important aspect here in this definition is that you'll see it says a draft of a diplomatic document, especially in terms of a treaty agreed to in conference and signed by the parties. So the signed by the parties here is important and agreed to. So when we use communications, we need to make sure that the devices on both ends are sending and receiving data that the other one understands, right? So the protocol basically sets out the rules for how does this protocol, how can they both understand it, and they need to be on the exact same page. One can't have a different understanding of it than the other. And so that's why we use that term protocol for communication protocols, basically setting out the rules for how does it actually work. So think about this. So what does happen if somebody doesn't follow the rules of a protocol? And this is not like a theoretical thought experiment. This is something that happens all the time. And it's not actually malicious a lot of the time. So can anyone think of an example of how two things could understand a protocol differently without any malicious intent there? Like uh, nobody necessarily did anything wrong. I know that might be a bit of a vague, kind of hard question, but
Well, wording in general can be Oh, I guess if it's protocol like on a computer, um, you could intend to send one signal and have somebody else intend to receive a different signal for the same measurement.
Yeah, so I think you're getting at exactly what I'm trying to get you to there. That basically you both will look at the contract, right? Or in our case, with a communication protocol, somebody will define this is how this communication protocol works, and then the different vendors will implement it in their equipment. But different people might read that standard differently. And so then they implement the protocol differently in their equipment. And nobody did anything wrong. Like it wasn't like somebody set out to screw with somebody else. It was just they, with their best effort, they interpreted the rules one way and somebody else interpreted it a different way, and then when the data gets to the other device, then they're going to interpret it incorrectly. And so then what you'll see very commonly is two devices from the same manufacturer will talk over a protocol just fine. And then you add in a device from another vendor, and then all of a sudden that one can't communicate to the other two. And so then people start blaming that new device that came in when realistically they might have even implemented everything correctly and the original ones didn't, but they implemented it wrong in the same way. So that's where it gets kind of weird is the protocols are like we set out these standards and rules for how the protocols work, and it's really, really important that they get followed correctly by the vendors. And there's a whole bunch of rules and tests and everything that they have to do to show that they definitely do conform to the protocols and standards. Um, because the communications will fail if they don't, or they'll operate in undefined ways. And so then this kind of question here is what is better, it to fail entirely or to operate in an undefined way? So I think the answer there is probably pretty obvious that it's complete failure is actually better, which I know seems a little weird sometimes, but because the unintended consequences of something, well, sometimes it's going to be better, sometimes it could be worse, but it's something you can't account for. Where if you know if you send a message and the other device isn't set up for that protocol correctly, they just won't receive it at all. You always know exactly what the issue is going to be. They're going to just get nothing. Um, so that's usually why we kind of set up these communications in general, where it's not like it works halfway. It either works entirely, everything works great, or it doesn't work at all. So that's kind of it's a feature, not a bug that you'll run into. So can anyone think of any commonly used protocols that you can see out there, just so make sure we're talking about the same thing when we're talking about protocols?
Goose.
Goose. Yep. So that's one that's in the 61850 standard we'll talk about during the next class.
Yes.
Anything else?
Mirrored bits.
What's that one?
Mirrored bits.
Oh, mirrored
Yeah.
bits. Yep. That's a protocol
SEL.
from SEL. Yep.
Yes.
So
The
those are both
MP3.
DMP3. Yep. So that one's yeah, another utility based protocol. But then protocol is also a very broad term. So there's a million different protocols out there. And like we use this same terminology, protocol, in every industry and even in just normal IT and everything. We have all these protocols that we use. Like, for example, in the web browser, not anymore, but you used to have to type in like HTTP before your web address. That's hypertext transfer protocol. Um, so again, it's a protocol. It's an internet-based protocol. So we use protocols everywhere. But I hope this kind of enlightened you a little bit and took a little bit of the scariness of the idea of a protocol away. That it's realistically the protocol. At the end of the day, that term just means it's defined rules for how these things are supposed to talk. That's all the protocol means. All right. So I did want to touch on proprietary protocols or proprietary communications in general, but more in the thought space of protocols because you will run into these in industry, and I just want you to know why. Like there are definitely benefits and there are drawbacks, and I want you to be able to make that informed decision when you run into this on the job. Um, so when I say proprietary, generally that would mean that a vendor has decided to make a communication protocol. And when they did that, they put a lot of work into designing it to work well, But then they also said like, hey, we made this, so you're not allowed to implement that same protocol unless you pay us royalty fees. And so that's where you'll see these proprietary communications where basically only one vendor's devices support it. So maybe like Siemens might make a communication protocol, or SEL makes a communication protocol, which I have an example down here. Title is one that's made by SEL, and only SEL devices will ever have title unless somebody else pays money to SEL to be able to put it in their own device. So there's obviously some drawbacks that you can probably immediately see from that, that if you use proprietary communication protocols, you can only ever buy the device from that certain manufacturer that made it, unless they license it to somebody else. But then also there can be other drawback of if that vendor ever stops even supporting that communication protocol, like they're just like, oh, we don't like title anymore. We want to move forward with something else. We're not even going to make any new devices that have that. Then you have to basically replace everything that you have because you can't talk in that communication protocol anymore. There's nothing else that exists to talk in it. So there's a lot of drawbacks, but one of the big reasons people do still use proprietary communication protocols, they generally work pretty well with that vendor's equipment because they design it in a way that's like it's very good for their space. So I'll use title again as an example. That's for sending analog information over digital communication systems very quickly. So if I wanted to represent the values of a CT, basically, so the current measurement to send over an Ethernet-based network, it can do, that's what title would do. So that is something like generally these communication protocols, like I said, they're going to work very well, but it's not advisable just for your longevity of your system, but then also working with all these other companies' components. So just for example, one that you might have run into in normal life is actually text messaging. That we had an original standard for text messaging called SMS, and that's how different cell phones could all send text messages, regardless of using like Android or Apple or whatever. But then some of the vendors wanted to send like more better messages, like with pictures or emojis, and so they started actually making their own protocols for that. Some we ran into some weirdness where certain phone vendors couldn't talk to each other, right? So like Blackberries was an early one where you could only talk to other Blackberries with some protocols, and then Apple had their thing where if you had a non-Apple phone, their messages would show up as like green versus blue, or like you couldn't see if somebody sent a certain emoji or something, it would look completely different on Apple versus an Android phone. And some of that was from them using proprietary protocol for sending text messages, APNS. But then there's a competing standard, which is RCS, which is basically an open standard that any phone vendor can use. And this is the basically exact fight that I'm talking about with like SEL title versus 608 sample values. This is an open standard for sending analog information, or the 62050 sample values is, and SEL title is proprietary from SEL. So it's the exact same idea, and hopefully that kind of helps you understand the market and everything, that it's there are reasons these proprietary protocols exist and there are reasons the open ones exist, and they're always kind of competing for market share. All right, so then the next one here, Ethernet, is the most incorrectly used term out there. And I will definitely be the first to say I use it incorrectly all the time too, just because it's convenient to do so. So the reason that this is very commonly used incorrectly is because people say it all the time to mean a physical cable. So they'll say like an Ethernet cable, meaning that kind of blue jacketed cable with a plastic end on it. They'll call that an Ethernet cable. Technically, that's wrong because Ethernet is actually a standard of formatting data, and you can use different types of cables to support Ethernet. So we want to avoid using the term Ethernet just to describe that one physical cable because it's technically wrong and it can confuse people when they're like looking at their overall design of their system. So in a household, it wouldn't really be all that wrong because basically all of your cabling is going to be that kind of blue jacketed cabling with the plastic end on it. But in the industrial world, we use other physical media as well, like fiber optics, which I have a slide on here in just a second. So again, it's very, very common for this to be misused. So I'm not telling you to go out there in the real world and anytime somebody says Ethernet, you're like immediately shut them down and be like, no, you're wrong, like you're using it wrong. People are going to do it and it's okay. But just make sure you're trying to use it correctly whenever you can. Um, so it is our most common method of transmitting data. So if we want to set up a network where we're sending data from A to B, 99.9% of the time we're going to be using Ethernet. That's kind of the default, but there are other communications out there that we use for certain reasons. So like if you're in the server world, there's like InfiniBand, and then in the utility world, we use like some weird hardwired stuff. Sometimes we'll even use like proprietary digital communications. It, other things exist, but we almost always use Ethernet, and that's why the term has kind of become ubiquitous with the cabling because it's what it's used for 99% of the time. So when I say media types, these are the different physical media that you will actually see out there in the real world. So the oldest one is serial, and it is still out there. Unfortunately, like it would be nice if it died out at this point, but it is a reality that you're still going to run into it. Serial is very rarely used for Ethernet, and the Ethernet standard doesn't actually directly support like the serial type. So you, if we're talking about Ethernet communications, it's almost never going to be serial. If in terms of Ethernet, we generally use fiber optics and twisted pair copper, but there were some old coaxial cables on Ethernet as well. But generally, it's these two pretty much all the time. So if you're out there in the utility world and you see communications cables, if you see either of these, twisted pair copper or fiber, it's probably Ethernet. If it's serial, then it's something a bit older, normally UART based. So we have reasons why we would want to choose any of these. I'm not going to go way too in depth with this. This is something that we can, as people who've taken my class understand, we can talk about this stuff for a very long time. I'm just going to kind of give you just the high level points. So serial is old, and that's one of the reasons it's still out there, actually, is that utility world, we have a lot of old stuff kicking around. And so they didn't have cheap Ethernet, or sorry, cheap twisted pair terminations at that time. So they put serial on the equipment back then. And we still have relays from the late 70s and the 80s in plenty of substations. So that's where one of the reasons you'll see a lot of serial. But then also this other idea that it's usually point to point. So what I mean by that is it's usually like one device talking directly to one other device. You plug in the cable between them. So that makes it really easy to use. And then also cybersecurity risks aren't as big with that. So that's one of the reasons that even now serial is potentially still being used. But realistically, moving into the future, we want to always use twisted pair copper and fiber optics when we can. But it's Ethernet over both of these. So the reasons that we would use twisted pair copper versus fiber is that it's really cheap. It's easy to install, so I can run it without the termination on it through like all kinds of crazy bends in the walls and stuff like that. And then I get out this cable and I can pop one of these plastic ends on it really easily and cheaply. So I can do very complex network setups with just this type of cable. And then it's very, very common. So even most laptops and everything still have a twisted pair port on it. So then you can connect into an Ethernet network really easily. The fiber, on the other hand, is a lot better in a lot of ways, but along with that, we have some drawbacks. So it is very expensive, generally per foot, compared to twisted pair copper. That's one of the biggest drawbacks. It's a lot better now than it used to be. The price disparity used to be a lot more, but even now it is still definitely a thing. But fiber optics can transfer much higher bandwidth. We'll talk about the specifics between bandwidth and latency here in a minute, but basically you can send more bits per second. So you can send a lot more information per second, generally with your fiber optics. It can run really long distances. So a twisted pair copper cable, generally you're limited to about 100 meters, which is 300 feet, where with fiber optics, we can even run like hundreds of kilometers or I don't know, tens of miles, I guess. Actually, I don't know. I know 100 kilometers is a standard for fiber optics, but if I converted that to miles, it's probably like 60 something miles. It's a long ways. And the reason it can do that is because it's not affected by electromagnetic interference, basically. So that's one of the biggest drawbacks sending information over copper is that if you have anything that's like creating a strong magnetic field, it's going to disrupt that signal. Fiber optics, the information is actually sent with light on the in the actual cable there, and from that, it doesn't matter how strong the electromagnetic interference is, it can't affect the signal in any way. So that's why it can run so much longer distances and then also can run right beside high voltage power lines and it doesn't matter. So we like to use fiber if we can, but there again are drawbacks. One of them being it's expensive. The other really big drawback to fiber optics is that they're very fragile. I can take a twisted pair copper cable and I can throw it in my bag. I can throw it on the floor and stomp on it. I can bend it really small and I can do all kinds of crazy things. It'll almost always still work. Fiber optics, you bend it like where it's at a 90 degree or like make it touch itself, then it's going to basically be broken, guaranteed. The inside is either glass or plastic. And you know how when you bend glass or plastic back and forth, it develops that like white line and then snaps at that location. You do that once with a fiber optic cable, it's done. It's broken entirely. So those two reasons are kind of why we don't use fiber optics like in the home. We still use copper, and that's going to be true for a very long time. Most, I wouldn't be surprised if we never really see fiber optics show up in home use, but we use them in utilities a lot because of the no electromagnetic interference. So, any questions on that? I know that was a lot of information really quickly.
Can we use the, I have a question.
Mhm.
So can we use the mix of twisted pair and fiber optic? It doesn't disrupt the signal.
No, you can definitely use a mix. Like a lot of high-end switches will actually have both twisted pair ports and they have these other ports called SFPs where you have an additional adapter you put into it, but they'll support fiber optics. So it's really common for a switch to actually have both physical twisted pair copper and fiber optic communications coming in. And you'd use the twisted pair for your local connections to your local devices, and then the fiber optic port for a long run back to like a main hub or to another switch.
Okay, thank you.
Yep. All right. So this is the other really big topic I wanted to mention today. I think we're going to run out of time before I finish all the slides. But this is the other big terminology that a lot of people use incorrectly. So Ethernet's number one, but then latency and bandwidth are number two, specifically because of people using the words fast, which I don't like. If we're talking about network communications, avoid using the word fast and avoid using the word speed. An S is really hard to draw with a touchpad. All right. So why, or can anybody describe the difference between latency and bandwidth? Or I guess the first question would be, which one of these do you purchase from your internet service provider for your house? Do you purchase latency or do you purchase bandwidth?
The latency, yeah.
Oh, you add.
Bandwidth.
Bandwidth, yes. So basically, when you buy internet from your internet service provider, you're paying for bandwidth, and whatever latency they give you is what they give you. You don't get to make any choices on that at all. And most of that's because they're generally giving you a latency that's good enough, and then you just want as much bandwidth as possible. And that's just because of what you're using at home. So the difference between latency and bandwidth is your bandwidth is how many bits of information you can transfer per unit time. So like if I want to send a bunch of ones and zeros, if I have like let's say 10 bits per second, I could send 10 ones and zeros in 1 second. And if I want to get something faster than that, I'd pay for more bandwidth and get 20 bits per second or 50 bits per second. But really what we buy from the ISPs now is up in the 100 megabits per second. So it's a lot of information. So mega would be million bits per second. So we get like really high numbers, but the bandwidth there is your bits per second. So then where does latency come in then? What would be the difference there?
Latency is the delay between sending and the other end receiving a signal.
Yes, exactly. So if we're buying bandwidth from our internet service provider, where would latency come in? Like when would latency ever be an issue then?
Latency can be an issue if, let's say you're in like a rural area and you need to connect to a meeting or something that's going to demand a lot of like real time. For example, there's like remote controls that you can operate from a computer. If you're trying to do that in a rural area, you'd have longer latency, which means it's harder to control things with such an input delay.
So you actually came up with a really good example there that I like. So you used one word that is really important there is the real time. That's actually a definition that we use very common in the industry where we'll say real time communications. We're actually talking about low latency communications. So that's good usage of that. But I actually liked your metaphor there, example with a like a video web conference call because that actually utilizes both aspects, bandwidth and latency. So if we're on a web call, like right now, like me teaching with you guys, right? What do you think bandwidth would affect in quality of what this interaction would be?
I can affect the quality of the video that you're sending. So if
Yes.
you don't have enough bandwidth, your video would come out really choppy, probably 4080p or 480p. Your audio would probably be pretty poorly sampled, assuming you have, a camera and mic that are good enough to sample at higher rates and, take better video.
Yeah,
Also,
exactly. That
screen
it's
sharing.
yeah, like I would look like really pixelated and be really low quality video if it was low bandwidth. But if I had low latency with the low bandwidth, you guys would still be able to like hear me fine. We could interact just fine. What would be the issue if I had high latency? Like what issue would you start noticing here?
I
Delay in responses.
Yes, delay in response, and especially when humans are talking to each other, that's something that's really difficult. There's a um, phone app called a Speech Jammer that was popular a while ago, where it's like if you played back somebody talking like 200 milliseconds later after they were saying something, it messes with their mind, and like you literally start losing the ability to speak. So latency with humans is like really, really important. So we need that low latency when we're having a conversation back and forth. Otherwise, we just constantly talk over each other and it doesn't work out. Um, so actually, a video conference is a really good example of showing the benefits of both of those things. That if I have low latency and but also but low latency is a good thing. Low bandwidth is a bad thing. So that's I guess they're kind of opposites of each other there. So but if I have enough bandwidth but not enough, but my latency is not good, then it would be you would see me clearly, but everything would be delayed. If I had bad latency but good bandwidth, everything would look crystal clear. Or I guess I already used that example. Sorry, I'm tripping over my words here a little bit. But let's kind of give an example that I like to use with latency and bandwidth is if we have a factory on one side of the country. So I'll just say this is like point A, and this is a factory. And then we have the entirety of the United States in between point A, and then we have point B, and we want to send trucks between point A and point B with raw materials, what would be the latency then of if we're sending raw materials from a plant at point B to a factory at point A? What would be the latency there? So it'd be how long it takes a truck to get from point B to point A. So if the factory at A orders raw materials from B, then if they know it's going to be 3 days before the truck gets there, you would have 3 days of latency. But what's important there to remember is the latency doesn't necessarily affect the bandwidth in that case. So on the factory at point A, they could order 10 trucks or 50 trucks. And then basically the amount of trucks that can get there in a per unit time is your bandwidth. So uh, the So if the first truck will not arrive for 3 days, but then the trucks will be coming in consistently after that. And so we can still have a high bandwidth connection even with long latency. But the important aspect that I want to get across here with this example is if we wanted to improve our latency in this example, what would we have to do?
Increase the speed of the signal propagation.
Yeah, exactly. We have to figure out how to get a truck from point B to point A faster, right? To improve the latency. And we can do that, right? We could do something like they could find a shorter route. They could have faster trucks, use higher, use the interstate so they can go at a higher speed, something like that. But in communications, that's not a solution that we really have because we're basically limited by physics. We're already sending a signal basically at the speed of light. So in terms of reducing latency, we don't actually have a lot of options. Most of our latency is actually caused by our networking equipment, like doing processing. So we can make that stuff faster. But once we've done that, we don't really have a lot of things at our disposal to get significantly faster. We're limited basically by the speed of light. But bandwidth we can deal with. So in that kind of example about like, okay, we can send more trucks. If we are limited in how many trucks can fit basically on the highway, what can we do to make it so we can send more trucks per day, per second, whatever? So we could add more lanes to the highway, basically. So we can do that same idea with communications, that we can just add more lanes for the data to be transmitted on. We could also buy cable that can fit more bits per second. Basically, like we can move to higher end fiber optics or something that can support more bits per second. But we can also just run a second cable, and then we've doubled our bandwidth. So bandwidth is really, really easy to fix, where it's like if we need more bandwidth, we can get more bandwidth. If we need lower latency, that's really hard. So I just want to make sure, kind of get the idea between those two that they're not easily fixed or both the same amount of easy to fix. But also people just use these terms incorrectly all the time. So just avoid using these terms. These are bad terms. So I don't like it if somebody says that their network is fast, because if they say it's fast, what do they mean? Do they mean it's high bandwidth or do they mean it's low latency? Or if they're saying like we're having problems with network speed, something like that. Like use the correct terms and be an engineer. So don't use these words. Use latency and bandwidth and use them correctly. And then basically I just had that text on there so that we already discussed here. All right, so then another term that you'll see very often is HMI. So that's human machine interface. Again, a kind of broad term that really you could use it to mean anything that interacts with a machine from a human. But usually what we actually mean it to be is any like a touch panel or anything on a specific device. So if you go up, like you go into a substation and then you see a display that shows you what all the power lines are doing, and you can click on something to say like have a relay open, open a breaker, something like that, then that would be an HMI, and that's something you can interact with. It's part of the SCADA system, and that's what they would be referring to with HMI. So there are some other terms that mean something similar, like GUI is something that's also used, but that's usually that's graphical user interface. That's normally used more in the like IT world. So we don't use that a lot in the utility world. Almost always it's HMI. So the design of HMIs is actually very, very difficult to get correct. And so that's something in industry, you're going to see a lot of really badly designed HMIs. It's something we spend a whole day on in my communications course, just because it is a very it's a very large problem in industry. And then sorry, I don't know if I can erase all my pen marks here. I know they're kind of getting, I don't know how I got the previous ones to disappear. Sorry about that. Yeah, I don't, if there's anything that's obscured by the writings here, just let me know. I can describe it, but yeah, the next term here is gateway. So again, this is something that's commonly uh, it's I would say people use this incorrectly quite often, but more just because they don't understand what a gateway actually is. So this one I do have a slide for in a few slides here where it's an image where we'll talk about like what is the gateway, and then I have another slide here for what a switch is, and then on that image we have like switches. So I do have some visual aids to go along with this, but I just wanted to describe overall a gateway first. So in terms of networking, you'll see something like if you're setting up your network configuration, a lot of times it'll ask you for your default gateway. And what that means is how do you want to leave your network? So like give me the address of the way to get out of here if I want to talk to things outside of my local network. But in industrial communications, it's not always defined that same way. So commonly we use it to just refer to any device doing a protocol translation. So I would set up something where I want to make it so that a DNP3 device can talk to a 62850 MMS device. I would buy DNP3 or 62850 MMS gateway, and then that would do the conversion in between them. I don't really like that terminology, but it's something that if you Google online, you'll find that as like hardware that you can purchase, and they'll call them gateways. So they're kind of propagating the bad terminology, in my opinion, but that's just how it is. So there are these two different terms for what a gateway is, but what you'll very commonly find is that actually they end up doing exactly like both of these functions at the same time. So where you're actually doing your signal translation is also the edge of your network, where it's like your substation is one thing where you're talking a certain communication protocol, and then your control center is talking a different protocol. Something needs to translate between them. It usually ends up being your gateway that actually does that. But that's also your way of exiting the network. So it ends up kind of being both at the same time. I think that's how that terminology originally kind of got mashed into one thing, even though those are kind of two different definitions. So you can kind of think of it as a bridge between two different networks. So like, for example, something you'll see all the time is that we use SCL real-time automation controllers where you can do a bunch of programming in them to do some really cool things. They're very similar to PLCs. We use those to act as the gateway in between like your substation and your control center or to like ISO New England. The other big term that we need to know for networks is your network switch or network switches. There's also routers that we have to worry about, but that's a bit more of a complex terminology, so we'll kind of leave that for later. So a network switch is what you're going to be utilizing most in your Ethernet networks to make things talk to each other. So theoretically, you can take a device with a twisted pair connection and another device with a twisted pair connection, plug them together, and they can talk Ethernet back and forth, but then they can't talk to a third party. So if we want to make a bunch of devices able to talk to each other, we need something to connect all those wires into, right? And that would be your network switch. So usually they have anywhere from 4 to 48 ports. So for your home network, you would probably have one that's only like 4 to 8. But when we're talking like substations, we buy these big 48 port switches. So we can plug 48 different devices all into this one switch. Everything can talk to everything else. Just in terms of cost, though, something you'll notice is for your home network, a normal switch that you might use costs anywhere from $10 to $40. And then an industrial grade one, like an 8 port, will cost anywhere from $100 to $5,000. So what do you think might be different between one that's going to be used for your home network and one that's used for industrial use? Like, why could it possibly be like 100 times more?
It's reliability mostly.
That's the really, really, really big one. Yeah. And because I've already mentioned that about like, we want to use SCADA now to replace some of these hardwired signals that have needed like really robust reliability. We can't do that if we don't have reliable equipment. And so that is absolutely one of the reasons that they're charging crazy amounts of money for even something that does the exact same functionality is the reliability. Another really big one is that they'll be environmentally hardened. So in a substation, you're going to have like 20 below 20 below 0 Fahrenheit temperatures. You might have 120 degrees Fahrenheit temperatures. You might have really humid environments, really dry environments. You might have like strong vibrations. There's all kinds of crazy things that can happen. And so there's also environmental hardening that goes along with this. And then the last big one is about industrial protocol support. So we need switches to support certain things. For example, precision timekeeping through PTP is something we utilize. That's something that's a functionality of the switch that it actually has to support that. There are very few switches under like $2,000 that support precision time protocol. So for industrial communications, if we need that thing, then we need to buy switches that support it, and then it can cost a lot of money. So just don't be surprised when you buy a switch for your house that's $40 and then you try to buy one for industry and you're like, okay, this is $5,000. What's the difference? So those are the differences. All right, and so then this is the diagram that I mentioned before. I really wish I knew how to get rid of all my writing on the screen, but oh, did I? Okay, now I got it. Okay, so I was drawing on the screen with Zoom um, rather than my slideshow software, so that's why it wasn't disappearing from the slides. Okay, there we go. So this is a diagram that I liked where it really shows the overall communication layout that you would see in a substation. And a lot of these things that we just talked about show up here. So for example, we have an RTU. So that's a real-time controller basically. So this is actually acting as our gateway and doing protocol translation. So we have these different protocols that are actually listed here, like 62050 Goose, MMS. We might also have like DMP3 here, but then the control center that's off-site, that's speaking some other protocol. And so then this is going to do a translation between those protocols, basically. But you also see this term here, SCADA server. So we could also just call this like a SCADA IED. We could replace these with IEDs if we felt like it. And then we have like a network switch. And so you see the switch is what everything is plugged into, and it allows everything to talk to each other. This stuff down here is something I'm going to be talking about next week, or yeah, next week, basically on Tuesday. That these are like where we're replacing hardwired signals with digital communications with SCADA. So right now in the real world, actually you wouldn't see these process level devices. This primary equipment would just actually be directly connected into these IEDs up here. But again, we'll talk about that more in detail. So if this looks a little confusing to some of you that have already done some of this, this is what it would look like in an actual digital substation. In the real world right now, this has one less step than this. So these would be connected directly into here, and that's probably what you've been working with so far this semester. So are there any questions on what you see here over, like in terms of what we've talked about already today? Anything that's confusing here? I know that was, again, a lot of information really quickly, but we have a couple minutes left, but we covered pretty much everything I wanted to today in terms of terminology. That is, I think that's the last slide. Let me. Oh no, okay, I have one more slide here. So this one other terminology is, and you'll hear me already use this probably on Tuesday and Thursday quite a bit, is that this is the idea of like IT versus OT. So IT is information technology, and you've probably already heard that in plenty of scenarios, right? So if you're at the University of Maine and your laptop breaks, they tell you to go to the IT department, right? So that's the computer guys. But when we're talking about things that are industrial grade, but there's still people that are doing the computer stuff, the server stuff, dealing with the networks, instead of calling them IT, a lot of times we call them OT. But they're very specifically not dealing with generally computers that people are using. They're dealing with industrial equipment. So that's where kind of the line is. So I posed one question here. Why do we generally have a different OT department than IT department? Even in like a utility where it has like they have substations, but then they also have people with computers and stuff. So a lot of times there ends up being an IT department and an OT department. Why are those separate people? Like, can you think of any reason?
Technology has more expansion, more equipment, more devices. That is complicated, and that's why we use more.
Um, yeah, I don't know if I would 100% agree. I definitely think both are doing a very complex job. But I would say probably IT actually has more equipment than OT, but OT has more industrial equipment, so it's different equipment needs. But basically, kind of what it's trying to get at here is that um, basically the IT and OT people, they don't necessarily have the same end goal. And so from that, a lot of the times, like you hear that quote to hammer everything looks like a nail. It's kind of that idea that IT people will try and apply their IT concepts to an OT network, and they are well intentioned. But the problem is we want like relays to talk to each other and RTACs to talk to the relays and things like that. And so we need them to do that very, very reliably in certain ways. Where with IT, what they're used to is like people utilizing the networks, and they have different needs and what they're doing. So a lot of times it ends up being actually that IT and OT concepts are not the same, even though we're both using network switches, we're both using servers, everything should be the same. It ends up being different enough that you do need those two different groups. And I think that'll become a little more apparent on Tuesday and Thursday of next week. Um, all right, so I've already pushed you a minute past today, so I'll leave you here. But any questions before we end it today? I was recording this. I don't know with the cutout from Zoom. Hopefully that didn't mess with anything, but I think Zoom handles it just fine. So the recording should still work just fine.
Do we have same session with you for in this coming Tuesday?
Yep, Tuesday will be on 61850 communications. So like basically how digital communications are affecting our design of substations. And then Thursday of next week will be like network commissioning. So how do we actually test a SCADA network for a substation before it gets put into service?
Okay, thank you.
Anything else? All right. Well, thank you everybody for attending. Sorry to keep you an extra minute. I will be home for the next like I'm flying on Tuesday again, so hopefully nothing else gets delayed, but I'm flying in the morning, so I don't think it should be an issue. I'll be actually home at my desk, so this will be a little smoother, no internet dropouts hopefully. So I'll see you all on Tuesday then, and thank you for attending.
Thank you.
Thank you. Have a good one.
Yep, you as well.